Let's go through an example. We set up a hypothesis test where the null hypothesis is the mean is 3. The alternate hypothesis, the mean is less than 3, so it's a lower-tailed test. From a long history of ride times, you know that the variance is 0.05 minutes. If the mean ride time really is 2.8 minutes, but you don't know this, a lot of these type 2 error problems are set up to be sort of hypothetical. What's the probability of a type 2 error, also known as beta, if a sample consists of n equals 5 rides? Well, let's take a look at this graphically. Remember, our null hypothesis is the mean equals 3, and our alternate hypothesis is that the mean is less than 3. Now, we're just supposing, we're making the assumption that the true mean really is 2.8, and what we're trying to find is beta if n, the sample size, is equal to 5. The first thing we need to do is we need to find this critical average. On the x-axis, this is x bar. We need to calculate a critical x bar below which we would accept the alternate hypothesis and above which we would reject the alternate hypothesis. The critical value is where we put alpha, and we're going to use 0.05 here. And we want to calculate the critical sample average below which we would accept the alternate hypothesis, above which we would reject the alternate hypothesis. So we're going to take 0.05 and put it into that tail to calculate x bar c. So let's go ahead and solve this in Excel. We can either use the norm.inv function, or we can use this formula here where we standardize. We use the percentage points z alpha of the standard normal distribution. I'm going to go ahead and use the norm.inv function. We're going to put alpha into the left tail. This would be different if you were doing a right-tailed test. The mean, we're basing this off of our null hypothesis, which has a mean of 3. The standard deviation is sigma divided by the square root of n, and therefore our critical x bar here is about 2.836. What this means is if we got a sample average of less than 2.836, we would accept the alternate hypothesis. If we got an x bar greater than 2.836, we would reject the alternate hypothesis. Now, if the alternate hypothesis really is true, H1 is true, is the true distribution, and if we get a sample average to the right or greater than x bar c, we have made an error. H1, the alternate hypothesis, really is true, but we're on the right side of x bar c. We have rejected the alternate hypothesis, and we have failed to reject the null hypothesis. And this region here is known as beta. Beta is the probability that x bar is greater than our critical value based upon the null hypothesis, but we're going to be basing that on our alternate hypothesis distribution, and the mean of that is 2.8. So this is how we can calculate beta. Beta is this dashed green region here. So let's go ahead and do this in Excel. Since this is an upper-tailed probability, x bar greater than x bar c, I have to do 1 minus. Now I'm going to use the norm.dist function in Excel. We're going to use our x bar critical. Our mean, we're basing this on the alternate hypothesis, that's mu1. The mean shifts, but the standard deviation stays the same. So sigma divided by square root of n. And this is cumulative because we want the area underneath the curve. And when I press enter, we get about 0.36. That means graphically this green hashed area is about 0.36, which means that the probability of making this type 2 error is about 36%. Now you can imagine you want to minimize the probability that you'll make this type 2 error. So you want to minimize beta. In order to make beta smaller, we can increase the shift in mean, the assumed shift in mean, but we can also make these distributions narrower. And that's related to the power of the test, which you'll be exploring in the next screencast.